Good day everyone and welcome to these lectures on settling and sedimentation. So, we will be continuing today also with respect to these lectures. In the previous lectures we studied that what are the different design conditions that we have to take care during the design of various settling or sedimentation basin, and we found that there are different non-idealities also which are possible during actual operation, and we have to take care of those non-ideal possibilities which may affect our operation. So, these non-idealities included like the turbulence and then the wind effect, and there are many other parameters that may account for the non-ideal behavior of the sedimentation basin. So, and also in addition to that we tried to understand the various design considerations in the inlet zone, settling zone, outlet zone and the sludge zone, and we also understood typical values which are used in the design of the actual sedimentation basin. So, today we are going to solve one problem and then we are going to learn regarding high rate settlers etc. In today's lecture itself. So, we will start with a problem continuing with the previous lecture. So, here the problem is given that we have to design settling tanks for a town which is having a common effluent treatment plant CETP with design overflow rate of 16 meter cube per day per meter square. So, we have tentatively the data is known to us that this is the overflow rate that we can have to use. Now, the maximum design flow which is possible as per the data available for that CTP is that we have to use the maximum value of 21,600 meter cube per day. Now, we are going to assume a water temperature of 15 degree centigrade. The column depth of the overflow rate was 2 meter where the design was done, and at 15 degree centigrade the viscosity of the water was found to be this. So, this is all these are the parameters which are known to us. Now, let us start with the design of the tank. So, this will try to cover whole of the design mostly. So, we will start with the what is will be the surface area which will be required if we directly consider this 21,600 meter cube per day of the flow. Now, the overflow rate is given and the total flow rate is given. So, the surface area we can find out by dividing the total flow rate with the overflow rate, and this is found to be 1350 meter square, and this value is very high as per the surface area. So, we cannot use a single design basin for this because this will be very huge otherwise. So, what we do is that we have to select the number of tanks we are going to use. So, the general criteria is 2 tanks is the minimum number, but considering this much high surface area we are starting with 6 tanks as a trial basis. So, for 6 tanks, suppose we have 6 tanks. So, divided by 6 we have 225 meter square will be the surface area for each tank. So, this is there. Now, we for this surface area we have to select the trial width for calculation as well. So, the maximum width for chain and flight sludge collector is 6 meter increment, and assuming a width of 4 meter. So, we are starting with a assuming a width of 4 meter. We now with 4 meter the length will be coming out, total length will be coming out to be equal to 56.24 because 4 meter is the width. If we assume the width to be 4 meter, this is there. Now, under this condition the L by W value, because L is known and width is known. So, this will come to 14.1:1. So, that is this value is larger than the 6:1 value which was given in the previous lecture. So, it may be considered acceptable and we may further go ahead and cross check whether you are meeting all the criteria with respect to design of a sedimentation basin or not. So, these are the length values. We are now going to take 56.25. The L by W where is already given. The area we have taken per tank is 225 and width is 4 meter. So, this is taken. Now, we have to take the trial depth. So, the column depth is a starting point for settling of the for designing the settling basin. Okay. So, an allowance for sludge depth of 1 meter is recommended. Now, in addition, the tank should be provided with 0.6 meter of the freeboard above. So, that also has to be taken care. So, since the depth was 2 meter for the column and we may start from there itself, and so overall if we see the it becomes 2 meter, 1 meter, 0.6 meter. So, that means it is 3.6 meter is the total depth of the tank, out of which the water depth is 3 meter, because 0.6 meter is the freeboard region. So, actual water depth is 3 meter. Now, if the sludge zone is not counted, the depth of the water is less than the design recommendation of 3 meter. So, this is okay as per that. So, because here we are taking care of the sludge depth as well. Now, cross checking with respect to length to depth ratio, it is 56.25 and 2 meter, because actual water depth is only 2 meter, 1 meter is for the sludge depth. So, side water depth was 3 meter. Now, the actual depth is where the water or settling etc. is occurring is 2 meter. So, under that condition the ratio is 28.125 is to 1, and this may be considered as acceptable. Now, what we do is that we go ahead and try to cross check that what is the velocity that is occurring when we are taking these values. So, depth is known, width is known, length is known, we have taken area is known. So, every parameter is now known to us. Now, checking the velocity. So, what will be the velocity that is there? So, if we perform the calculation, we will be finding that in terms of meter cube per second, the value is 0.25 is the Q, and the area which is there, which may give the idea with respect to velocity is, we have 6 tanks, each are having 2 meter depth and 4 meter width. Okay. So, first the total flow rate is divided by 6. Now, the whatever is the flow rate after that in the each tank, that is divided by the depth and the width. So, that we have the cross section is known to us. Now, cross section is 2 meter and 4 meter. So, it comes out to be 0.0052 meters per second. So, this is within the acceptable range of 0.005 to 0.018 meter per second. So, we are at a condition where the velocity is 0.0052 and it is also within the acceptable limit. Now, going further, we calculate the Reynolds number. So, this is very important that we calculate the Reynolds number, Froude number, and cross check that these values are within the acceptable limit or not. So, Reynolds number in the previous lecture we had studied is given by this equation. So, V as the flow velocity is already known to us. RH is the hydraulic radius, which is given by the area divided by perimeter. So, area is 2 meter deep, 4 meter wide, and the perimeter is, so we can tentatively cross check like this. So, this is like, and this is the length. So, this is what we are designing tentatively. So, this is the length, okay, and this is the depth and this is the width. So, this is known to us. Now, within this the perimeter will be width plus height plus height. So, 2 depth plus 1 width. So, we have 2 depth plus 1 width, which is 4 meter. So, this way the hydraulic radius comes out to be 1 meter for each of the settling basins, which are 6 in number. So, RH comes out to be 1 meter. Now, once this RH is known, we can calculate the Reynolds number, because we know the flow velocity, we know the RH, and we know the viscosity also, which is given in the problem itself, or which has been found separately. So, we can find it out separately by knowing the density and viscosity parameters. So, this is known. Now, this value is 3978. If you put all the values, we will calculate it to be 3978, and which is less than 20,000 and may be considered acceptable. So, this is there. Now, similarly, we have to calculate the Froude number also. So, Froude number, everything is known, velocity is known, hydraulic radius is known, and the gravity is also known. So, under that condition, we have, if we put all the values, this comes out to be very similar to 10 raised to minus 5 and can be considered acceptable. The acceptable limit is that the Froude number has to be greater than 10 raised to minus 5, and this is tentatively coming in the same range. So, this is there. Now, we have to go for the design of the launders also. So, the basic design condition which was given in the previous lecture was that we have to provide launders for 1/3 of the tank length. So, the tentative length of the launders is 1/3 of the tank length. So, we calculate it, it is 18.75, and we can place them at 1 meter intervals on center, so that we have, there are 3 in the tank. So, this is possible. Now, to check the wear loading, that the wear loading should be below 250 meter cube per day per minute, and so we have to cross check that what is the wear loading which is coming. So, provide, since we have provided launders 1/3 of the tank length and the flow rate was this. So, we have 6 tanks and 3 launders in each tank, and we have 18.75 is the length of the launders per launder, and we have 2 sides. Okay. So, taking all these things, the launder wear loading which will coming out will is 32 meter cube per day per meter, and this is below 250 meter cube per day per meter. So, this is also acceptable within the acceptable limit. So, this is there. So, if we consider, so all the parameters that we have taken, when we considered 6 number of tanks, they are coming within the, all the parameters are within the acceptable limit. So, we can go ahead with the design of this. We can optimize by this design by taking care of the cost factors. So, that is a possibility, but overall this design seems to be logical, and all the tick marks are there with respect to design criteria. So, overall design was that the flow rate was this 21,600 meter cube per day or 0.25 meter cube per second. The number of tanks were 6, and the width of each tank has been taken as 4 meter, length has been taken as 56.25 meter. The L by length to width ratio was this, and depth including the sludge zone etc. was 3.6 meter, and the overall without considering the sludge depth, this was the ratio which was there. The velocity was also within the 0.0052 within the limit. Reynolds number was 3978, Froude number was 10 raised to minus 5. The launders, 3 launders were used which are spaced linearly, and the launder length is 18.75 meter. The wear loading is 32 meter cube per day per meter, and which is also within the limit. So, overall this is the design, and we can use for this design. So, this is the one typical design of a sedimentation basin for some flow rate, and this sedimentation basin has to be used in a CETP, common effluent treatment plant. Now, going further, now the high rate settlers have coming into picture a lot in all the industries, common effluent treatment plant, effluent treatment plant. And so, what are these high rate settlers, why they are used, what are their advantages as compared to traditional settlers. So, this we are going to understand now. The sediment to optimize the sedimentation basin, it is very important that the flow, how much amount of water we can process through the sedimentation basin within certain time limits. So, that has to be taken care. Now, the term high rate settlers is actually meaning that we have very high amount of water can be processed within a specified time. So, there are basically two types of settlers which are coming as the high rate settlers. These are like parallel plate settlers and tube settlers. So, in the parallel plate settlers, shallow settling devices, they are consisting of stacked offset trays are there. So, we have parallel plate, we can tentatively we have one plate, second plate, third plate, etc. And then tube settlers, certainly where we have different tubes which may be there, they are all closely spaced and the flow rate is all through these tubes. So, these tube settlers are there. So, basically two types of high rate settlers are very common, tube settlers and parallel plate settlers. So, we are going to learn regarding both of them now. Now, already discussed high rate settlers are two types, plate settlers and tube settlers. What they do is that they increase the available area for solid settling. Okay, this is one thing. Then there is a second thing, when what they do is that they decrease the depth. So, that means the depth that the particle has to settle while moving through the settler is very less. So, that means they can settle quickly. Actually, the earlier the design was that suppose this is the simple horizontal flow settler. Now, any particle which is entering here, the earlier consideration was that it should settle down, before actually it leaves. So, this is there. So, that means the time this depth is less. So, that means under that condition the time of settling will be much less. So, more amount of and the time of settling will be much less, and under that condition if that time of settling is lower, we can increase the flow rate, because we want the target to reach the surface area on which the settling is occurring. As soon as it reaches this particular area, we can increase the flow rate, so that the particle is not coming out, still the flow rate is very high. So, that is possible. So, by decreasing this depth, we are able to increase the horizontal flow velocity also. So, that means we are able to increase the throughput also of the water which can be processed through these high rate settlers. So, this is there. So, one of the key thing is that they have very high available area for solid settling. In a detention type of less than 20 minutes, they have settling efficiency comparable to that of a settling tank which may be having a detention time of 2 hours. So, that means and this is because the depth for which the settling has to occur is much lower here in this settlers. So, this is there. Now, understanding each of them one by one. So, first is the tube settler. So, water to be clarified passes upwards through the tube. So, you can see the pictures here. Okay. So, through this the water to be processed will pass in any of these tube settlers. So, they may be of different dimensions. So, the water has to pass through them. Now, as settling occurs, the solids are collected on the bottom of the tube. So, all the solids will get settled on the bottom of the tube in each of the tube. Now, these tubes are inclined at an angle of 45 to 60 degree, and which is actually steep enough to cause the settled sludge to slide down the tube. So, this is possible, and because of this steepness they are able to settle and they slide down also. The sludge falls from the tube to the bottom of the clarifier, where it is removed by the sludge rakes. So, this is there. So, the sludge will fall from the tube to the bottom of the clarifier and which is further removed. Now, the tube cross sections may be square, rectangular or other shapes are also possible. The high overflow rates 3 to 6 times as those used for conventional settling can be used to achieve the same degree or higher degree of treatment. So, this is possible. Laminar flow is one of the important considerations in the tube settler for efficient settling. That is true for other settlers also. So, these are the different cross sections which are possible: square tubes, these are simple circular tubes, then we have rectangular tubes, rectangular with layers alternating the direction. So, we can see here some layers are also there in between. We have hexagonal or chevron type where there is some inclination is there. So, the sludge may easily settle and come out here in chevron tubes. So, these are all possible. Some design criteria for tube settlers are there, is that the design is based upon the total projected surface area of the tube. So, this is important, already we do this. The surface loading rate of around 1.2 meter per hour for aluminum iron base coagulants can be used. So, it may be 1:2 is the range for this surface loading rate for tube settlers. The inlet condition turbulence causes uneven flow distribution to the tube. So, this has to be avoided, and the sludge falling from the tubes must be able to settle to the tank bottom. So, high velocities may cause high shear rate. So, this is there. So, this also has to be taken care of. Now, in the inlet condition, to avoid the turbulence, stilling zone of around 25% of the total basin area should be left. So, this is there. So, to avoid this turbulence we have to take care of this, and minimum depth of 3 meters should be left below the tubes. So, this is another one of the, from experience this criteria has come. Now, effluent design, a clear space of 2 to 3 meter above the tube must be provided. Launder should be placed less than 1.5 meters from the center. So, this is there. Solids removal, solids can be removed from the same type of equipment as used in the conventional sedimentation unit. So, these are the some important criteria for tube settlers. So, they have very design equations very similar to earlier, not very difficult to design, but there are some key design elements that we have to take care. Now, second of the this high rate settler is the plate or lamella settler. The sedimentation tanks are commonly divided into layers of shallow tanks. So, what is done is that overall the sedimentation basin may be like this, okay, D is the depth. Now, what is done is that this is divided into a number of layers. So, depth has decreased. So, it is now D1 only if we consider like this. So, the depth will decrease. So, we have layers of shallow tanks. So, this is there. So, the settling depth is decreased tremendously. The flow rate can be increased while still obtaining the excellent particle removal, and this is because the time of the settling has decreased. So, that means we can have higher flow rate, so that the still the particle cannot go out of the length, and if they can reach to the end also, this is okay. So, that can be taken care by choosing a higher flow rate in such a manner that the sludge does not leave the system, but still the particle settles down. So, that is there. The flow rate can be increased while still obtaining the excellent particle removal efficiencies. A lamella decrease the distance a particle has to fall in order to be removed. So, this is what is the key thing in the plate settlers as well as in the tube settlers. Now, similar to the inclined tube settlers, except that the inclined plates are used to form the settling compartments. Here again the inclination is there. Sludge and water flow is concurrent in the same direction. The flow entering a lamella, a separator flows downwards between the plates, depositing the sludge at it travels. So, it is in the same direction we are moving, the flow, the sludge and water both move in the same direction. Now, in a horizontal flow tank, the front 1/4 length of the basin is generally free from settler modules to allow for better inlet flow conditions. So, we have to take care of this important criteria while designing the lamella or flat settler. Now, this is how it is shown. We can see here they are inclined also in one of the direction. So, this way the flow may there, alternating cross flow lamella settlers is there. So, we can see the difference is there. Then horizontally projected area, this area which is there. So, this is the key thing, we remember that the top area is one of the important parameters in the design of the sedimentation basin. So, we can see here, so the area has been reduced because of this inclination. So, that helps in the overflow rate. Now, some design criteria is that the typical loading rate range from 0.7 to 1.7 meter per hour, which corresponds to 5 to 15 meter per hour for overall basin loading. So, we have to take care this. Co-current flow is applied, then inlet distribution is very critical and that has to be taken care. Landers are placed on the order of 1.8 meters. Submerged orifice may be used to design to create head loss to enable proper good flow distribution out of the system. Then orifice velocity may be in the 46 to 76 centimeter per second range, and chain and flight or bottom track units are generally used for sludge collection. So, this is there. Now, suppose we have 20 million gallon per day capacity of the water has to be treated. So, conventional sedimentation basin will require area which is given here. Okay. So, this is the area which will be required by conventional sedimentation basin, whereas if we use the plate settler, only this much area will be required. So, we can see clearly lot of land space can be saved in the same for same capacity, or if the land space is same, we can use very high amount of water can be treated in the plate settler in place of the conventional sedimentation basin. Now, so this is the benefit, we have lower cost with respect to land, certainly construction cost may be comparable, building and maintenance cost are important criteria. So, they will depend upon various parameters, but land cost is certainly saved. So, this is there, and maintenance is also not that difficult as compared to others. So, the performance, we have increased treatment efficiency in the plate settler, they improve the water quality, they improve the hydraulics over conventional settling or tube settler design. So, this is the importance of plate settlers, have these advantages which are there, and they are more durable and less prone to clogging than the tube settlers, because tube settler the sludge moves in the opposite direction, it moves in the sludge direction. So, we can easily remove the sludge also, and there are modular designs which are available. So, we can always just by basic calculation we can tentatively cross see that which is good enough. It is like a modular design are already available. So, cost has been already reduced a lot. So, we can always go for plate settler very quickly, okay, until unless we have very high throughput which is required. So, under that condition we can go for tube settlers as well. So, all these possibilities are there. There are many design considerations, many design options also in both tube settlers, plate settlers, etc., and based upon that we can select the plate settler or tube settler. Now, plate settler has been used for in potable water treatment, backwash water recovery, wastewater treatment, in most of the industries. In new construction also they are being used. They are also being retrofitted to the existing basin where we have to treat more water, and they are coming in a package treatment systems also. So, they have lot of advantages and they are now highly being used in the industry. So, these are the references that we have used all throughout this settling and sedimentation section, and in this sedimentation and settling section we have understood that after coagulation and flocculation, sedimentation basins are very important and they have to be used to settle out all those particles which cannot settle normally or during less time. So, normally they will take very high time. So, in the sedimentation basin they can be settled down quickly. Now, there are different types of behaviors which are possible, and that depends upon the concentration of the particles in the water. So, they may be discrete settling, they may be flocculent settling, they may be there may be hindered settling, there may be compressive settling. Now, for all these conditions there are different design equations, different theories have been given, and basic methods by which we can tentatively get the basic design data has been shared in these lectures. So, we have understood all those things. After that we came to know that okay, there are different types of settling basins which are used in wastewater treatment plant. That may be in the grit removal, that may be in the primary treatment, that is there in the secondary treatment after the biological treatment. These type of settlers are very common in anaerobic digesters which are used in the our common residences also, which are far away from any city or otherwise. So, all these places we have settling operation which is going on. So, we should have a basic understanding of settling basin or sedimentation basin, and based upon the ideas, the theories and the design considerations which had been discussed, we can tentatively design the sedimentation basin and we can use it as per our requirement. So, and the behavior is very important, that what is the solid concentration we are going to treat in that sedimentation basin. So, we will end the sedimentation section with these lectures. After sedimentation, because the smaller size particles or less denser size particles still cannot be settled out, because we always design the sedimentation basin to a particular diameter of the particle, suppose 100 micron, 50 micron. So, we always decide that which is the key diameter we are going to target for removal. So, anything below that will be carried over, and that has to be separated in a, if the turbidity is not within our requirement, if still the separation has not been good enough, we have to further treat the water via the filtration mechanism. So, we will start with the filtration mechanism in the next lecture onwards. So, today we will end the sedimentation section. We will continue with the filtration sections in the next lecture onwards. So, thank you very much.